I'm Aly Cabral, one of the product managers on the core database server. And I have Jason Carey with me, a lead engineer.
Hi.
As you guys know, MongoDB is developing multi-document ACID transactions. Well, MongoDB is a distributed system, so applications that are backed by MongoDB can scale out automatically as the data grows beyond the size of one node, and they can automatically be resilient in cases of node failure. However, the implementation of transactions in distributed systems requires non-trivial coordination and consistency across these nodes that standalone systems just don't have to worry about. We wanted to deliver transactions without sacrificing the rest. But we didn't get here overnight. The engineering effort and the path to transactions has spanned many years of engineering effort. There's been many projects along the way that are interesting and fundamental to transactions, and one of those is logical sessions, which is what Jason is going to talk to us about today. So I'll pass it over to Jason.
Great, thank you. All right, so as Ellie's saying, I'm talking about logical sessions. It's a feature that we deployed in 3.6 that enables a couple of interesting use cases and is sort of an important part of our long-term transaction story. And I guess I want to sort of start off with talking about what transactions are, how they're represented, and then walk through a couple of use cases for where we're using them in 3.6. And as I'm going through those use cases, I'll talk a little bit about how they're implemented and what's sort of interesting about them in our system. And so let's start from the top. Logical session IDs are very lightweight identifiers that we can tag to other sort of resources and operations in our system. And they're made up of two major parts. The first is an ID, which is a globally unique identifier in sort of like, as the technical term GUID, i.e. a range of bytes that are generated generally from a source of randomness. There's a couple of different schemes to generate them. And they're meant to be something that you can generate local to your machine and still end up with an identifier that is never going to collide with any others that are generated in your distributed system. And then secondarily, we also have a UID that is a SHA-256 digest of your fully qualified username. And so this means that clients, they're generating the ID portion, but they're always fully disambiguated from all other clients. This has some sort of important security and practical implementation details that I'll talk about a little bit later.
Right, and it's important that the clients are able to generate these IDs from a performance perspective, right? So you don't have to reach out to the server in order to get this ID.
Absolutely. We wanted you to be able to use logical session IDs with every kind of operation in the server in 3.6. And so we didn't want to add more than just the 48 bytes of sort of overhead that this scheme is providing, and avoid you having to go to a centralized server or synchronize or do extra round trips, anything like that.
Great.
And so that gets us to our sort of first use case, which I'm calling easy administration. And so in order to really describe what I'm talking about, I'm going to walk through a little bit of MongoDB's sort of deployment architecture as a distributed system, a couple of common use cases in that system, and what logical session IDs bring to the table that wasn't there in 3.4. And so to begin with, I want to talk a little bit about the two kinds of distributedness that exist in MongoDB. The first one has to do with high availability, and it has to do with ensuring that data that you write to our database survives any particular node failure. And so we call these replica sets, and they are what's inside of these boxes here. And you'll notice that we have three things called MongoDs. In this case, those are database server processes meant to live on different physical nodes. And some of them marked S and some marked P. There's one P in each particular set, and that indicates a primary, where the others are secondaries. And it's worth emphasizing that being a primary or secondary is an ephemeral state for a node. It isn't something that you're started with at startup and live with forever. Rather, nodes sort of all start out equal, and there's an election that takes place where one of them becomes the primary, and thus can change over the lifetime of the cluster during node failures or network partitions. And so that's a replica set, and this is the way that we ensure that you don't lose data. We write to a primary and then replicate that data from primaries to secondaries, and once your data is on a majority of those nodes, you can understand that even in the event of node failure, your write will still be durable. But there's another half of the story. What if you want to store more data than fits on any single physical host? And that's where sharding comes in. Where replication provides a set of nodes that all have not exact copies, but have full data sets. Sharding instead means that the individual shards have slices of the overall data. And so the way this works is that you have your app, and so that's one of these red boxes up here, and you'd, let's say, like to do a write. So this is you're writing a document for the first time. So you go out, and your write goes to a MongoS, and then it picks some shard where it's going to write the data based on a routing table that's available to all of the different MongoSs. So it's going to write your data there. Then later on, you might come through and you might talk to a different MongoS that has the same routing table, and you might want to read the data back. And sometimes the data that you're reading isn't necessarily on the same nodes. This is sort of distinguished based on a shard key that's in either the document that you're saving or maybe in the query that you're using. If your query can be, you can figure out which shard the data will go to. You don't have to talk to all of the shards. You can talk to just the ones where the data could live. So you might have a read that goes out to these two particular shards.
So this is a query that might span multiple documents that don't necessarily all live on the same shard.
Absolutely. And one of the things that these reads do is that they, well, first, so they do two things. They open two types of interesting sort of artifacts on the servers. One is that there are jobs that are running. We call these, well, operations. And so you might have an op. And then additionally, you can have, and these are things that are actively running. So it might be an administrative command that you're in the middle of executing, or it might be about going to disk and fetching the I/O to actually do the work of the query.
So those are the ops.
Absolutely.
Active.
And then secondarily, you have these other things, which I'll call cursors. And a cursor is sort of, can be downstream of an operation where we do a find, open a cursor, and then to fetch successive batches, you issue get more commands against that cursor, which return you more information. And so the cursor has both a batch of data to return, as well as instructions about how to get the next batch. And cursors are going to sort of be interesting a little bit later, and so I'll keep those in mind. And I'm going to talk right here about how things work in 3.4 in the event that something goes wrong. So let's say that you start off a command that you thought, or a find command that you thought was actually going to be easy because you were planning on targeting an index. And then you realize that you actually screwed up, and now you're talking to all of your shards, and you're scanning through all of their data. What you can do can be more or less limited. And in particular, you're in a bad place if your MongoS just goes away. Maybe it crashes, something else happens. Now each of these cursors, they're just gone. There's no way to really talk about them. Assuming that you set a timeout on them, they will eventually time out, but that'll happen individually. And an enormous amount of work might occur to fill them up with their first batch of data. And there's no way for you to get at them. And one of the big things the logical sessions adds in 3.6 is that all of these commands now, this write path, and then also these reads, they're now tagged with a logical session ID. And so that means along with all of the messages that we're sending into the server, along with the regular payload, we also have the logical session ID. And that means that these cursors and these ops are now tagged. They're not regular cursors, they're cursors annotated with a logical session ID.
And you can list session by users, right? Like you can list your sessions that you have by user ID?
In a certain way, you absolutely can. There's sort of an implementation detail that I'll get to a little bit later about the global notion of the sessions table. But you can also look inside of any particular MongoD, and you can list all of the sessions for running operations that are available there. It's the $list local sessions aggregation stage. So you can use that, for instance, to find all of the sessions for a particular user if you'd like. Absolutely. And what this allows is it allows you to go ahead, and now we have the exact same scenario where we have this read command that was going off, it's going off the rails. Maybe you typed it in manually from the shell, and you realize you've made a mistake. Now you have a way of cleaning it up. What you do is you issue a kill sessions command, and you can kill either by a specific session or all of the sessions for your user. And that'll propagate a kill command that will go to, or let's say in this case, let's say this was an errant process, and this app is your shell. Sorry about that. Just talk to one of them. And we're going to do a kill command. And this kill is going to go out to every single one of these shards. And it's going to say, please kill this logical session ID. And it's going to find all of the operations that are in those processes that have matching LSIDs. And they're going to, if they're a running operation, cancel them. If they're a cursor, close them. And so in this way, it's very easy in 3.6 to ensure that work is always cancelable, it's always stoppable. You don't necessarily have to have the same sort of administrative privileges to do this work that you need in 3.4, where we've sort of lost track of who owns these objects. And so you need someone, like, you have to go find a DBA to fix your problem. Now you can fix it yourself. And so that's the story that we're calling easy administration. Which leads us on to sort of our second story, which feeds into more what logical sessions means to transactions and to other parts of our system, which is distributed garbage collection. And so in the same way that you might want to target some of those resources, be they long-running ops or long-running cursors, you may also want to be able to clean them up automatically. And today, there's only a local notion of timeout. For instance, you can make cursors that have timeouts or don't have timeouts, but they time out based on work that happens on those individual nodes rather than work that's happening anywhere in the system. And so in order to fix that problem, we've introduced a new notion. Here we have a client and a MongoDB process, and by process I mean a MongoDB or MongoS anywhere in the system. And then we have a thing over on the side called a sessions collection, and we're going to leave that sort of a little bit ephemeral for the moment, but I'll come back around and fill that out. And so for every wire protocol message that a client makes into a MongoDB process, they pass an LSID, a logical session ID. And the controller records that they did this, and on a 5-minute interval, it goes out and syncs it to the sessions collection. And so what this means is that using a session in MongoDB updates sort of a global state for that session. And the thing that we're updating it with is over here. It's the LSID, which is your logical session ID, and also a last use time, which is a timestamp. And the last use time is important because our sessions collection also has a TTL index on that last use field. And we use that to track all of the logical sessions that are more than 30 minutes old, and we actually delete them at that point. And what that means is that other controllers on other processes can look to that global sessions collection, and they can see if the sessions that are associated with the long-running objects that they have inside of their process, if they have a record that's in that global sessions collection, even if no one's used them locally recently, they know that they're still in use somewhere else. And this is super important for transactions, because there is a new piece of state that we've added in 3.6, which is when you do a write, now in addition to some of the other artifacts, you can also do a retriable write. And a retriable write, I won't talk about that feature too much in this particular presentation, but retriable writes allow you to check whether or not you actually did a write if in the event of a network failure. And there's a little bit of state that lives on every single node that was involved in a write. And so let's say you did like an update across many nodes, or you inserted many different documents. It's possible to see where it actually landed or not. And we have to keep state around in order to make sure that that retriability, that promise can still be honored. And so but we still want to clean up that state. We don't want to keep it around forever. And so we use this distributed garbage collection mechanism in order to ensure that we can actually clean up that retriable write state when the session that was doing the retriable write actually finishes.
So the controller is a local view of the sessions I've seen. The sessions collection is a global view of all the active sessions in the cluster. The last use time is the time that the session was last reported by a controller to be active.
Absolutely.
So that would be like on a 5-minute cadence, right? So it's not the precise time I last used that session, it's the last time someone reported my session in use.
Exactly.
Okay, great.
And yeah, so in addition to being able to clean up retriable write state, this fixes another long-running problem we had, specifically with aggregation in sharded clusters, where we're trying to assemble some complicated piece of data where we may not talk to any particular shard for a long period of time because we're doing some work or returning results from another shard. And so generally you had the choice of either making sure that your query finished everywhere within a relatively short time frame, or setting the cursors to no timeout, where you would risk losing track of them in the event of a failure. And so this also sort of closes that out by giving all cursors that run under a logical session an implicit timeout of the session lifetime. And yeah, that's sort of how logical sessions work in our system, and we have plans to add more transactional state to this distributed garbage collection mechanism, and it gives us a real level of confidence to know that as we develop more distributed features, we can keep track of the lifetime of these objects with one core sort of central mental abstraction, rather than having to solve it on sort of a per item basis.
Awesome. Well, thank you, Jason.
Thank you.
Appreciate the time.